Let us now discuss Chapter 1 of Differential Equation. A differential equation, abbreviated as DE, is an equation involving an unknown function and its derivatives. A DE is one which contains within it at least one derivative, and sometimes, for analytical convenience, the differential equation is written in terms of differentials. It may also be given in the explicit or implicit form. Examples of differential equations. We have A, dy over dx is equal to 2x plus 5. B, d square s over dt square minus k square s plus a is equal to 0. C, x square plus y square dx minus 2xy dy is equal to 0. D, du over dt is equal to h square times the quantity d square u over dx square plus d square u over dy square. Letter E, the quantity d square w over dx square raised to the third power plus xy dw over dx plus w is equal to k. And we have F, the quantity d cube s over dt cube square plus s ds over dt plus 2st is equal to 0. And letter G, y double prime plus the quantity y prime square is equal to y. As you all know, y double prime can also be written as d square y over dx square. Now, let us have the classifications of differential equation. A differential equation may be classified as to the following characteristics. Letter A, the order. The order of a differential equation is the order of the highest order derivative in the equation. Letter B, degree. The degree of a differential equation is the largest power or exponent of the highest order derivative present in the equation. And letter C, the type. A differential equation may be ordinary or partial as to the type of derivatives or differentials appearing in the equation. That is, it contains ordinary derivatives. It is an ordinary differential equation. And if the derivatives are partial, the equation is a partial differential equation. Example. Consider examples A to G. This. So, based on their characteristics, what will be the order of A to G, the degree, and its type? So here are the answer. For letter A, dy over dx is equal to 2x plus 5. Its order is 1 because we only have a derivative present in the equation of order 1, meaning we have first derivative. The degree is 1 because the first order derivative that we have in here only has a first degree. So, first degree pa rin siya. And the type is ordinary. Letter B. We have d square s over dt square minus k square s plus a is equal to 0. In here, the order of the differential equation is 2 since we have a second derivative in the equation. This is of the second order. Its degree is still 1 since this is not raised into any other power but 1. Okay? And the type is still ordinary. Letter C, the quantity x squared plus y squared dx minus 2xy dy is equal to 0. The order is 1. And the degree is also 1, since we have first derivative. And then let us have letter D. Letter D has an order of 2. And this is based on the second derivative present in the parentheses. Okay? So we have a second order derivative in the equation. Therefore, the order of the differential equation is of second order. Letter D has a degree of 1. Since none of these second order derivative is raised to any other power but 1. Letter E. For letter E, the degree is 2. Why? Because we have a second order derivative here, or second derivative, d squared w over dx squared. The order therefore is 2. Now, what will be the degree? The degree is 3 since our highest order derivative present in the differential equation E is raised to the third degree. Here. So, the order is 2, the degree is 3. And for letter F, the order is 3. Why? Because the highest order derivative present in the equation is of the third order. D cubed s over dt cubed. This determines the order of the differential equation. How about the degree? The degree is 2. Since our highest order derivative present in letter F is raised to the second power, or second degree. Now let us have the last one, letter G. For letter G, the order is 2. Why? Because we have y double prime. And y double prime can also be written as d square y over dx square. This is also y double prime. And this is of the second order. Therefore, the order of letter G must be 2. How about the degree? Even though y prime is raised to the second power, y prime is not the highest order differential in the equation. Y double prime is the highest ordered differential in the equation. Therefore, this determines the degree. The degree of y double prime is 1. So, that will be the characteristics of the differential equation in example. Okay? So, let us have the solution for differential equation. But first, let us have the general form of the nth ordered ordinary equation. Since the scope of the course will cover only the solution to ordinary differential equations, it is important to define its general form. The following functional notation is to be adapted as the general form of the nth ordered ordinary differential equation. So we have this equation 1.0. This is the general form of the differential equation in nth order. Solution to ordinary differential equation. The solution to an ordinary differential equation is another equation free of any derivatives or differentials. expressing the functional relationship between the dependent and independent variables, and which, when substituted into the equation, reduces it to an identity. Example: the solution of the second-order differential equation y double prime is equal to 6x plus 4 is any of the following. Any of this equation should be or would be the solution to this equation. Y prime is equal to 6x plus 4. So those are y sub 1, or the first possible solution to the equation, is x cubed plus 2x squared. Y sub 2 is equal to x cubed plus 2x squared minus 3x plus 5. Y sub 3 is x cubed plus 2x squared plus ax. Y sub 4 is equal to x cubed plus 2x squared plus ax plus b, where a and b are constants. So, types of solution to an ordinary differential equation. So we have two types of solution to an ordinary differential equation, and these are particular solution. So what is a particular solution? The solution to a differential equation is said to be particular if it does not contain any arbitrary constant. So, the differential equation, or the equation, must be free of any arbitrary constant. So what are the arbitrary constants that we are talking about? Arbitrary constants are the c that we add whenever we integrate an equation. So as we integrate, if you will recall in your integral calculus, as we process the integration, we always add c at the answer. This c compensates on the difference between the left and the right of the equation. That is why we always add c. Another solution to differential equation is the general solution. So what will be the general solution to differential equation? The solution is said to be general if it contains at least one arbitrary constant. Okay? So, on our first topic, other than the introduction, we have the elimination of arbitrary constant here. In practice, differential equations arise in many ways. There is one way of arriving at differential equation, however, that is useful in that it gives us a feeling for the kind of solution to be expected. We start with a relation involving arbitrary constants, and by elimination of these arbitrary constants, come to a differential equation consistent with the original relation. In sense, we start with the answer and find the problem. So meaning, we will be given the answer and find the problem. Meaning, we have given the integration of the solution and will return that back into its differential form. Okay? So let's have example number 1 on the elimination of arbitrary constant. Okay? So we have example number 1. Eliminate the arbitrary constant C1 and C2 from the relation y is equal to C sub 1 e to the negative 2x plus C sub 2 e to the 3x. Okay. To eliminate the arbitrary constant, we have to differentiate this equation given to us twice. Take note of this. If the arbitrary constant present in the equation are 2, we need to differentiate the equation 2 times. If you only have one arbitrary constant, meaning you have to differentiate this 1 time. If you have 3 arbitrary constant in the equation, you have to differentiate this 3 times, and so on. So let's start. So what is the first derivative of y is equal to c sub 1 e to the negative 2x plus c sub 2 e to the 3x. So we have y prime, or the first derivative, is equal to negative 2 c sub 1 e to the negative 2x. And the first derivative of the second term of the equation is 3 c sub 2 e to the 3x. As I've told you a while ago, we have to differentiate this twice. So what will be the second derivative of the equation? We have y double prime is equal to 4 c sub 1 e to the negative 2x. So this is differentiation, and you have discussed this in your differential calculus. So we have plus the second derivative. So we have 9 c sub 2 e to the 3x. So how can we eliminate the arbitrary constants c1 and c2? We have to do algebraic work on this solution. So we need to use the solution to the system of linear equation in algebra. So let's call this equation number 1, equation number 2, and equation number 3. We need to combine equations. Say for example, let us combine 1 and 2. So we have equation 1, y is equal to c sub 1 e to the negative 2x plus c sub 2 e to the 3x. And equation number 2, y prime is equal to negative 2 c sub 1 e to the negative 2x plus 3 c sub 2 e to the 3x. So in order for us to eliminate one of the arbitrary constants, we need to, say for example, we want to eliminate c sub 1. We need to multiply equation 1 with 2, thus giving us 2y is equal to 2 c sub 1 e to the negative 2x plus c sub 2 e to the 3x. Ayan. Okay? And just copy equation number 2. So we have y prime is equal to negative 2 c sub 1 e to the negative 2x plus 3 c sub 2 e to the 3x. Oh, I forgot. This should be multiplied to 2 also. Then add. This cancels out. So we have y prime plus 2y is equal to 5 c sub 2 e to the 3x. Call this equation 4. Okay? Now let's combine this time equations 2 and 3. So equation 2, we have y prime is equal to negative 2 c sub 1 e to the negative 2x plus 3 c sub 2 e to the 3x. And y double prime is equal to 4 c sub 1 e to the negative 2x plus 9 c sub 2 e to the 3x. Since in the combination of 1 and 2 we have eliminated c sub 1, we might as well eliminate on the combination of 2 and 3 the arbitrary constant c sub 1 also. So, in doing that, we need to multiply the second equation by by 2. So we have 2y prime is equal to negative 4 c sub 1 e to the negative 2x plus 6 c sub 2 e to the 3x. Then just copy equation number 3. Y double prime is equal to 4 c sub 1 e to the negative 2x plus 9 c sub 2 e to the 3x. Then again, add. So we have y prime plus y double prime is equal to, this cancels out, 15 c sub 2 e to the 3x. Call this equation 5. So let us now combine equation 4 and equation 5. So equation 4 is y prime plus 2y is equal to 5 c sub 2 e to the 3x. And then we have equation 5. This is 2y prime. 2y prime plus y double prime is equal to 15 c sub 2 e to the 3x. Okay? So, we need to multiply equation 4 by negative 3, giving us negative 3y prime minus 6y is equal to negative 15 c sub 2 e to the 3x. And just copy equation 5. So we have 2y prime plus y double prime is equal to 15 c sub 2 e to the 3x. Again, add. So this cancels out entirely. So we have y double prime minus y prime minus 6y is equal to 0. We now have an equation free of any arbitrary constant. And if you'll notice, we have a differential equation. So from the solution to the problem. So this is example number 1. Now let us have example number 2. So what is example number 2? So example number 2 is eliminate the arbitrary constant a from the equation. This is number 2. Eliminate the arbitrary constant a from the equation x minus a square plus y square is equal to a square, where a is your arbitrary constant. Okay? So, we only have one arbitrary constant present in the equation. That is letter A. So we need to differentiate this once. So what will be the differential of this equation? If we're going to differentiate this, we have 2 times x minus a plus the differential of y squared. This will be bring down to y dy or y prime. And the differential of a constant, since a is a constant, is 0. Simplifying this, we have 2x minus 2a plus 2y y prime is equal to 0. Or we have 2a is equal to 2x plus 2y y prime. A is equal to x plus y y prime. We still have your a. It is not being eliminated. What we need to do now is to substitute this value of a into the original equation. So we have x minus a. But what is a? A is x plus y y prime plus y squared is equal to a. But what is a? X plus y y prime squared. Okay? This is now an equation free of any arbitrary constant since we don't have a in the equation. So this is the solution to number 2 problem. Next, example number 3. Eliminate beta and alpha from the relation x is equal to beta cosine of Wt plus alpha. Take note that W here is a parameter. Okay? So parameter and need not be eliminated. So we only have to eliminate beta and alpha. Okay? So we have 2 arbitrary constants here, beta and alpha. So we have to differentiate the equation 2 times. So what will be the first derivative of the equation? Meaning dx over dt. That is the parameter t. So what is the first derivative? So for cosine, beta cosine Wt plus alpha, your u here is Wt plus alpha. So what will be our du? Your du must be W dt. Okay? Since alpha is a constant, the derivative of this is 0. So we only differentiate this term. Okay? So beta, again, by the way, what is the derivative of cosine u? This is sine u du. But what is u? The derivative of cosine u or cosine Wt plus alpha is equal to sine Wt plus alpha w dt. So, applying this in the first derivative, we have w beta sine Wt plus alpha. Okay? But what will be the sign? The sign must be negative. So the derivative of cosine u is negative sine u. Okay? Negative sine u. So this must be negative. That will be the first derivative. How about the second derivative? D square x over dt square. We only need to differentiate this once again. Okay? So again, your u here is wt plus alpha. The second derivative, therefore, must be negative w square beta. The derivative of sine is positive cosine. Cosine wt plus alpha. So we have the three derivatives that we needed. But take note, equation 1 and 3 both has cosine function in it, whereas equation 2 has sine in it. So it is both proper for us to combine 1 and 3 and instantly find the solution to the equation. So let's combine 1 and 3. So we have x is equal to beta cosine wt plus alpha, and d square x over dt square, or the second derivative, is equal to negative w square beta cosine wt plus alpha. So we needed to eliminate beta and alpha. Therefore, we have to multiply the first equation by equation number 1 by w square, giving us w square x is equal to w square beta cosine wt plus alpha. And just copy equation 3. D square x over dt square is equal to negative w square beta cosine wt plus alpha. Adding